All right. Okay. Hold on. How's your assignment one? Okay, so far. Is due this Friday, right? 30th, I think. 30th, let me check. 30th by 5. Yeah, 30th by 5. Okay, don't forget to submit online on the e-learn system, right? Okay, let's continue with recombination. So in the last class, we have discussed about three types of recombinations briefly, and we've covered radiative recombinations details. And today, let's continue with radiative and the other two recombination, and hopefully we can finish the rest of the topics under this section. Okay. Right. Radiative recombination. We also call it as band-to-band recombination, and as a result of the recombination, we have photons emitted from the semiconductor material because of direct band gap semiconductor. Okay. On the other hand, if we have a non-radiative recombination like SRH or OG recombination, we're going to have heat dissipated as a result of the recombination, right, instead of light. So for radiative recombination, the recombination depends on the density of available electrons and holes. Okay, so the rate of the recombination is proportional to the density of carriers, electrons and holes. So both types of carriers need to be available in the recombination process, of course, because they will recombine with each other. So you need them to be present. So the rate of recombination is proportional to the product of N and P. Okay, the rate is proportional to the product of N and P. Right, at thermal equilibrium, recombination rate equals to generation rate. We've discussed this one before. At thermal equilibrium, since there is no net recombination or generation, where G is equal to R, okay, at thermal equilibrium. The recombination rate is given by U-rad, or recombination rate, equals to B, or bimolecular recombination constant, a constant, times the product of NP minus Ni squared. Okay, NP is the carrier, the density of electron and holes minus Ni squared. So recombination constant here is 2 times 10 to the 15 centimeter cube per second. And if we talk about low-level injection, we've discussed briefly about low-level injection. If we talk about N-type semiconductor, where majority is the electron and minority is the hole. Majority electron, minority is hole. So we're going to look into this concept later on when we discuss about p-n junction, about the minority carrier. So for low-level injection, the recombination rate will be given by the very same equation taken above, but you have to expand the value of P, okay? So you still have to use B and P. B is bracket NP minus N squared, but the NP here is expanded, where you use the very same value of N, but your P is expanded into P and naught plus delta P, okay? P and naught is the minority carrier, minority hole concentration in N-type material at thermal equilibrium. Remember last time we discussed about P and naught or MP naught. You have to mention three facts, okay, when you talk about P and naught or MP naught. For example, if you talk about P and naught, So that belongs to density of free holes in n-type material at thermal equilibrium plus delta P. Okay, plus delta P, right? And delta P here is the excess carriers introduced into the system. Okay, and this calculation can be simplified further to B times delta P, because P and naught is way smaller than delta P, times N, and also can be equated to delta P over tau H, or lifetime of the hole as the minority carrier, where tau H is equal to 1 over the constant times the density of electron. Okay, so similar expression can be derived for p-type semiconductor as well. What we have to do is reverse um, the representative here. Okay, so instead of expanding the p, you have to expand the n, and p remains the same, and down here the delta p will become delta n over tau e. Okay, and tau e is also equal to 1 over b times p. So you reverse everything. Ya ada somebody calling. Sorry ya, anak saya call dekat sekolah. Where was I now? Hold on. Okay, can you see the slides, right? Can you see? Okay, good. Okay, so you can do the very same thing for for another carrier as well. Okay, so this one. Oh no, hold on. Sorry, yeah. Okay. Right, so let's move on to the second one, SRH recombination or Shockley Hall recombination. So we're going to have Shockley Hall recombination when we have defects in our semiconductor, okay? It doesn't matter whether it's in the bulk or it's on the surface. So as long as you have defects in your semiconductor, you will have SRH recombination, okay? So it's also called non-radiative recombination, and named after these three guys, Shockley, Reed, and Hall, back in 1953. So impurities and defect result in deviation from the perfect lattice. So the moment you have undesired impurities, so we've discussed last time when we talk about the early introduction of the course. So the moment you have undesired impurities, it will cause distortion to the lattice, right? So the original lattice is perfect, but the moment you introduce something else, some foreign materials into the lattice, is no longer perfect, right? So this may result in defect formation. So defect, if you look under the scope or under SEM, you can look at the physical defects, but they are physical in nature. But if these defects are translated into electronic states, they are actually trap states in the band gap. Okay, so you're not supposed to have anything in the band gap, but due to the presence of the impurities or defects, you will have impurity trap states in the defect. You're going to have electronic states. Maksudnya is going to have an energy level in the band gap, right? So you're not supposed to have this, but due to the defects, you're going to have this. So defects near mid-gap are almost effective recombination centers. We discussed one last time, where we have seen that some defects are shallow in nature. Shallow here means the electronic states or the energy level is near to either conduction band H or valence band H. Okay, so these are called shallow states, shallow trap states. On the other hand, you can also have deep level defects which appear close to the middle of the band gap, just like what we see here, somewhere near the middle of the band gap. Okay, so they are, in this case, effective recombination centers for our carriers. So shortly Hall recombination, SRH recombination, occurs via two-step process. We've seen last time in the animation where your electron drops to the trap state and then eventually drops to the valence band hole. Okay, and dominates in long lifetime material. So we're going to learn about the concept of lifetime after this. The excess energy due to the recombination of SRH is given to the lattice as heat. Okay, that's why we call it as non-radiative. In the first case, we have seen radiative, where the excess energy is emitted as a photon during recombination or upon recombination, but in this case, the excess energy due to recombination is given off as heat. Surface of crystal is a defect, give range of states at surface within the band gap. So if you look at, for example, your samples or, well, your device or your materials, your semiconductor materials, if, for example, you have defects physically can be seen, or maybe they are not visible at all, they are physical in nature. Maksudnya you can see that particular piece, small, a couple microns, a couple nanometers on your sample or within the sample, or the impurity already diffused into the sample. They are physical in nature, but they appear as an electronic states in the band gap. Okay. Defects are physical, but they appear as electronic states in the band gap. So the moment you have electronic states in the band gap, you're going to have SRH recombination. So it occurs via bulk defects or traps, right? So the density of the defects given by NT, and the energy level is ET, right? Single trap recombination can also be described by electron capture and hole capture, because what they are doing is they are capturing electron or capturing hole from the semiconductor material or from the device. So the net recombination rate for trap-assisted recombination is given by this equation. It's very, very complicated one, a long one, but they can be simplified if the energy level of the trap states is equal to the mid gap. For example, if your trap states lies right in the middle of your band gap, so this is your EC, this is your EV, say this one is your EI, right? The E intrinsic, the original one. But if your energy level of the defect happens to be the same as EI, so ET equals to EI, so you're gonna simplify this equation, because you're gonna have ET minus EI equals to 0, since they are the same. Okay, so the exponential component is going to be simplified, and this equation is going to be simplified to the below equation, right? but still, it's still not it's still not simple in nature. It's still complicated in nature if you look at it. Quite long though, but it's not as complicated as the above one. But if your energy level, if the energy level of the defect is not the same as the intrinsic energy level, then you need to use the same equation as above, right? So for low-level injection in N-type semiconductor, you can also do for P-type, but for N-type, so this becomes NT times VTH. VTH is the thermal velocity times hole capture. This one is the hole capture. Sigma E, sigma H represent the electron and hole capture cross section. So in this case, it's simplified to hole capture cross section times excess carriers of the electron, delta P, and it can also be equated to delta P over tau H, lifetime of the hole, where tau H is equal to the inverse of 1 over nt times thermal velocity times hole cross section. Right, the third one is called Auger recombination. So remember, it's a three-particle process, also non-radiative. So it can be an E process, EEH, or can also be an EHH process, air process. So you can either have two electrons in the conduction band and one hole in the valence band, or two holes in the valence band and one hole in the conduction band, right? So it can be either one. So one conduction band electron recombines with a hole and passes the excess energy to the second electron in the conduction band. Then this is called E process, right? So this is happening in the conduction band. On the other hand, it's called EHH process, where it happens in the valence band, right? Upon recombination, the electron passes the excess energy to the second hole. Instead of to the second electron, now it is to the second hole in the valence band, right? This one is VB process in the VB. First one in the CB, second one in the VB. So EEH CB, EHH VB. So the excited second carrier, either electron or hole, is called hot carrier. I did brief you a little bit about application of hot carriers, and it's not limited to only solar cell, also applicable to some other application as well. But this is the principle of hot carrier effect, where you try to harvest the energy possessed by the second carrier before it thermalizes back to the band edge, either a conduction band or valence band, right? So the process most important in heavily doped semiconductor. So this process, the Auger recombination, only happens if you dope your semiconductor to above 1017. Okay. So if you dope at 1014, you're not going to have any Auger. Okay. So if you dope at 1018, then you're going to have Auger recombination. So if you look at the three types of recombination, radiative, SRH, or Auger, it depends on the condition of your semiconductor material. Okay, so not necessarily you have all at the same time, or you may only have like one at the same time, or only two at the same time. Well, it really depends on what type of semiconductor material, what is the doping level, does it have defects or not? Okay, so you have to really look at the condition before you will be able to tell whether which recombination takes place. Auger recombination involves three particles, so either EH or EHH, an electron and a hole, which recombine in band-to-band transition and give off resulting energy to another hole or electron, right? So we've seen this one just now. Okay. So the net recombination is given by above. So CE and CH is density of electrons and holes. Auger recombination rate is given by this. Later on, when we do a calculation, it will be more clear. It'll be more clearer, right? Okay, this is another simplification for for the case of N-type semiconductor, okay, you can use the same, what you call the same cases as what we've discussed in radiative and SRH. So now let's look at lifetime. Total lifetime is related to the lifetime of carriers, right? The moment you generate your carrier, you generated your carriers, you want to know how long does the carrier survive? Okay, how long in terms of time? Okay, in terms of time. So the total lifetime. So kalau if you want to describe lifetime, it's the duration between generation and recombination. Okay, this to this in terms of time. So the time it takes, dia macam jangka hayat lah, jangka hayat, the lifetime of a person, for example, since birth until the hari kematian lah, until he died or she died, right? So generation until recombination. So the time span, the lifespan of the carrier, either electron or hole, is called lifetime, right? The lifetime of electron or lifetime of hole. So the total lifetime is given by 1 over tau total. So 1 over tau total, which is equal to 1 over tau, 1 over lifetime related to radiative recombination, plus 1 over lifetime related to Auger recombination, plus 1 over lifetime related to SRH recombination. So, for example, if your semiconductor material has only 2 dominant recombinations, say you have gallium arsenide heavily doped without defects. You dengar ambil description. Gallium arsenide heavily doped without defects. So what sort of recombinations do you have? Okay, Auger, ada lagi? Gallium arsenide. Look at my material, heavily doped, no defects. So what are the dominant recombination mechanism from these 3 characteristics of the semiconductor material? If you want to relate to the total lifetime equation, what do we have? Okay, Faris said Auger. Auger due to, Faris, due to what? Why do we have Auger in this material now? Okay, can unmute yourself. Kenapa kita ada Auger in this case? Faris? Bukan heavy effect, heavily doped, right? Heavily doped. So it depends on the doping. So if you want to check this, katalah kita ada checklist, you have this checklist. So this heavily doped, so you're gonna have Auger already. So Auger is on. So Auger, kita ada Auger now. So what else? So no defects. No defects means what? Do we have SRH? Tak ada SRH, tak ada SRH. So no defect, therefore there's no SRH. No SRH component in the equation. Gallium arsenide. So do we have radiative recombination? Gallium arsenide? How do you tell? How do you tell whether gallium arsenide has radiative recombination or not? Look at the band gap. Direct band gap, therefore, since it is a direct band gap semiconductor, so does it have radiative component? Does it emit photons at all? Yes, right? So yes, okay, good. So because it's direct band gap, so you're gonna have radiative component, dominant radiative component. So in this case, if the question says you have gallium arsenide heavily doped, no defects, so your total lifetime is going to be dominated by 1 over tau rad plus 1 over tau Auger only. Okay, there's no defects component in the equation, so therefore you can just omit the 1 over tau SRH because of the absence of the defects. So let's move on to the second example. What if, look at this total lifetime equation, what if we have crystalline silicon, lightly doped, full of defects? crystalline silicon, lightly doped, full of defects. So now your total lifetime becomes what? What do you get for total lifetime equation? Crystalline silicon, apa tadi? Lightly doped, light, just write down light, light, defective, defect lah, full of defects. So what do we have? Okay, so it's a crystalline silicon, direct or indirect band gap. Indirect kan, so therefore the radiative is not dominant. Okay, so kita boleh potong radiative. Then OJ, is it lightly doped? It's not. It's lowly doped, right? Or lightly doped. Therefore, there's no OJ component. So kita hanya ada. Now we are left with full of defects, right? Only. So the dominance ni actually is relative, right? It's relative to each other, of course. If it's not that high, then maybe it won't affect as much. But if it's in the middle, the value, you may have to include the component as well, just to see how does it affect the whole equation, okay? So the process with the shortest lifetime dominates the tau total. So the process, either OJ or SRH or radiative, which one has the shortest lifetime, so that will affect the final lifetime of, or the total lifetime of the total recombination time, okay? The total lifetime of the carrier. So, okay, so you have to look at the equation, right? So now we learn about concept of lifetime. So now from lifetime, we're going to learn about another concept called diffusion length. So diffusion length is the very same as what you learn at lifetimes now, generation to recombination. But now instead of the time, it is about the distance. The distance, let me put it as L, as the equation says L. The distance traveled by electron or hole from the point it's generated until the point it recombines. Okay, so the distance passed through by that electron or by hole is given by diffusion length. So lifetime is proportional, diffusion length is proportional to the lifetime by this equation. L equals to square root of d times tau, where L is the diffusion length, the distance traveled, and d is the diffusivity of the carriers, and tau is the lifetime that we learned in the previous page, right? So L is equal to square root d tau, okay? So definition, the average length or the distance, if you like, travel, a carrier move between generation and recombination. Sama aja. So if you talk about lifetime just now, it's still the same thing, but the dimension is time. Okay, when you talk about diffusion length, it's the same thing as well, but the dimension is distance, right? So semiconductor materials that are heavily doped have greater recombination rates and consequently shorter diffusion length. So if you dope your crystalline silicon, say at 1018 versus 1014, the diffusion length of your 1018 crystalline silicon will be a lot lower because the lifetime of the carriers will be a lot lower as well. Because if you go back to the previous page, if it's heavily doped, then you're going to have a low, high contribution from the OG that will reduce your lifetime. And if your lifetime is reduced, your diffusion length will be reduced as well, because L is proportional to tau. Okay, higher diffusion length are indicative of materials with longer lifetime, and therefore an important quality to consider in semiconductor materials. So usually in when you talk about manufacturing or research, when you talk about a material with high quality, or crystalline silicon, or gallium arsenide, or phosphide, or material, whatever, if you talk about high quality semiconductor material, we are talking about material with high lifetime. Okay, so typically the order of like 100 is in order of hundreds of microsecond, maybe. Not necessary, but just to give you some idea. Okay, so it can be somewhere 100 microsecond, or it can be millisecond. can also be down to nanosecond. It can also be lesser than that. So you want to have a material, a semiconductor material with high lifetime. Okay, high lifetime maksudnya your carrier is going to survive long enough, and the carrier is going to travel long enough through the material before they are collected by PN junction or by metal contacts, right? So we can conclude that if your material is of high quality, so it's going to have high diffusion length and high lifetime as well, right? On the other hand, if the material has poor quality, it's going to have a low diffusion length and low lifetime. So therefore, it's indicating the material quality that we are using for materials for our devices. So this is an example. If you look at the lifetime diffusion length on the y-axis, primary and secondary axis, and donor density, which is the doping level for ND and NA, the donor and acceptor on the x-axis, right? So we can see that generally we have reduced carrier lifetime and diffusion length at higher doping level. Okay, if you go for higher doping level, so you're going to have lower lifetime on the black one is going to be lower on the, okay, because here you're going to be low, and as a result, since L is equal to square root the tau, so the L is going to be lower as well. Okay, sama, because both of them are proportional to each other. So the same goes to the acceptor as well. So when the lifetime is lower at higher doping level, the diffusion length will also be lower since L is proportional to tau. So when you are operating your semiconductor device later on, when you need your device to be heavily doped, for example, you need to be aware of how much lifetime and diffusion length are you sacrificing, because later on at device level, we're going to see when you dope your semiconductor material high, you are going to reduce the series resistance in the device, which is good to form contacts with metals in order for the carriers to be collected to the outer circuit. But when you dope your semiconductor high enough, even though your resistance drop, your lifetime is going to be dropped as well. So when we optimize our semiconductor material, or when we fabricate a semiconductor material, it's always a juggle between getting the right resistance, low enough resistance, and a high enough lifetime or diffusion length. Okay, since if you go for high doping, you're going to reduce resistance, but you're going to suffer from low diffusion length or low lifetime. But in order to recover the lifetime or diffusion length, you need to reduce the doping level. That will increase your series resistance. Okay, so nanti kita akan tengok at device level where you need to compensate the doping level accordingly so that you have both series resistance in the device that is sufficient for your device to operate at optimum condition, and also you can extract your carriers with sufficient diffusion length and lifetime, right? So you cannot simply go for heavy doping to reduce resistance without looking at other factors, or you cannot simply reduce the doping level just to have good lifetime, good diffusion length without taking care of the series resistance in the device. Okay, so it's always a juggle between both. All right, so recombination, let's finish it off. We are almost done. Okay, we're almost done. So recombination, when you talk about recombination, OJ, radiative, or SRH, so the recombination can happen in the bulk or at the surface, okay? In the bulk or at the surface. So if I draw a cross section here of your semiconductor material, so say this one is crystalline silicon, katalah single crystal silicon. So recombination in the bulk means the recombination is happening somewhere in the silicon, in the volume of the silicon. So that is meant by bulk recombination, right? This is bulk recombination. On the other hand, if you talk about surface recombination, we are talking about recombination that happens right on the surface of the device or on the semiconductor. So that means it can happen here, can also happen here, right? Kat tepi ni kurang lah sebab it's usually very thin, but this one is like quite a big one. if you're operating like the wafer that I showed to you last time, 6 inch by 6 inch, so the whole surface of 6 by 6 inch squared may have surface recombination, front side or rear side, okay? So recombination rate is limited by the rate at which minority carriers move towards the surface. So in this case, it's surface recombination. So when the carriers move to the surface, either to the front side or to the rear side, it's gonna be associated with a surface recombination velocity. How fast does the carrier move to the surfaces, front or rear? And we call this as SRV, surface recombination velocity in centimeter per second, used to specify the recombination at the surface. So when you talk about high SRV, so if you're talking about high SRV, we are talking about high recombination rate at the surface. So high recombination rate, huh? So I put it U rate at the surface. If you talk about low SRV, on the other hand, then we are talking about low recombination rate at the surface. Okay. So then, do we want to have high SRV or low SRV in our device? Do we want to have high SRV or low SRV in our device? Do we want the carriers to rush to the surface to recombine, or you want to stop them from recombining at the surface? What do you think? Anyone? Do you want them to, if I can give you this analogy, if your carriers run to jump into the drain, and on the other hand, you want to stop them from going into the drain, do you want them to be in the drain or not? They're going for annihilation process. Gone. You'll be gone. So the carriers will be gone. Do you want them to recombine or not? What do you think? At the surface? No idea. You don't want them to recombine, okay? You don't want them. So you want to have low SRV. You don't want to have high SRV. We're going to see later on a device where this is going to be more clearer, okay? So in a surface with no recombination, the movement of carriers towards the surface is zero, but ideally, you can say it's zero, but in practical cases, we won't have zero, but we will be able to have low SRV, but not zero. So if you have ideal case, your SRV will be zero, but in the real case, no, okay? But you want to have low SRV in all cases. In a surface with infinitely fast recombination, the movement of carriers towards the surface is limited by the maximum velocity they can attain, and for most semiconductor in the order of 10 to the 7. So you can have your SRV as high as 10 to the 7. In typical devices, usually in the thousands. Okay, if it's low, then it's usually below 100. It can be a couple of hundreds as well. So how to minimize? Okay, how to minimize? So how do we minimize recombination? It's actually, it can be tackled by a process. So the reduction of the number of dangling bonds and hence surface recombination is achieved by growing a layer. Okay, hold on. If you need to relate this to the properties of a crystalline silicon wafer, for example. So remember last time we did discuss about before you get your silicon wafer, you need to grow an ingot, right? Ingot. Then you slice the ingot into wafers. Okay, so the moment you slice this ingot into wafers, at the surface on the front side and rear side is going to be there is going to be termination of lattice. Lattice tu akan kena potong, right? You cut the lattice, you chop off because you want to have separate wafers. So the termination of lattice results in formation of dangling bonds. Dangling bonds on the surface. Maksudnya you're going to have like bonded bonds that are not satisfied, bonds that are not fulfilled on the surface of the front side and also on the rear side. And the moment you have these dangling bonds on the surface, they will induce surface recombination on the front side and also on the rear side. Okay. So to be able to fix the surface recombination, we need to do a process called as surface passivation. I'm going to give you extra notes later on the passivation. So usually for silicon process, for crystalline silicon, so katalah ada dangling bond macam tak satisfied, there's no complete bonding. So these dangling bonds appear as defects in the lattice. So when you talk about defects, they are SRH recombination centers, right? So they then need to be fulfilled. That you need to have bonded. You need to have some bonds to have them satisfied. You have to introduce bond. So normally this is done by amorphous silicon deposition on the crystalline silicon, or you can also do passivation using hydrogen. Okay, in order to terminate, in order to remove the termination of the lattice, you need to sort of rebond again. Okay, so it's called surface passivation process. So how does it help? So the lifetime of the material is contingent upon the concentration of minority carriers. So the moment you can reduce, the moment you do the surface passivation, you are actually reducing the SRV. Say before passivation, your SRV was like a couple of thousands. So after the passivation process, your SRV may go to say a couple hundreds centimeter per second. So it will lessen the rate of recombination. So less carriers will be depleted on the dangling bonds or near dangling bonds due to the SRH recombination. So if this can be minimized, the lifetime of the material can be extended. So say if you have your dangling bonds, your lifetime is in nanosecond, for example. The moment you've done your passivation, it may go up to say microsecond. So from 10 to the 9 second, it goes up by 3 orders of magnitude to 10 to the 6, 10 to minus 6, 10 to the minus 9 to 10 to minus 6 second. So that means your lifetime has improved due to the presence of passivation. So not only the surfaces, the front side and rear side, you can also, since the defects can also be present in the bulk also needs to be passivated. So that's why we need bulk passivation. And this is typically done by hydrogen in the silicon process. So these are some equations that we've learned before. So we're going to learn this Poisson equation when we talk about p-n junction later on. And we've also discussed about this current density equation when we talk about carrier transport phenomena, which is dominated by drift and diffusion of both carriers. Okay, continuity equation and some symbols. Right, so this is what we've covered so far. So a bit of a revision, you can have a look at this, intrinsic condition, law of mass action, dope semiconductors for p-type and n-type, and minority carrier population. We've discussed this one last time. When, say, if you look at on the right hand side where your Na is 16, your P should be 10 to the 16 because it is a majority carrier. Hence, the minority carrier, which is the electron in p-type, will be 10 to the 4, right? Given by law of mass action, 10 to the 20 divided by 10 to the 16, which will give you 10 to the 4, and you can then relate back to this. Okay, so that's all for today. I'm going to give you some references on passivation later on eLearn. And tomorrow we're going to continue to p-n junction. Okay? All right, okay so far? I need to run to the school now to pick up my children. Okay, huh? Right. So I'll see you tomorrow then. Bye-bye. Take care. Assalamualaikum.